Hello. My name is Hong Chan. I am from SK Telecom, which is the largest telecommunication company in Korea. Today I'm going to introduce our Spark use case, focusing on network quality analysis and prediction with geospatial visualization. Actually, the co-speaker and I am not fluent English speaker, so please hold the question until the end of the talk. And we have a code demo booth with Intel. So if our explanation is not enough, then you can visit us. We can talk without time limitations. Okay, let's get started. First, I'm going to show you a brief demo. This demo will visualize network quality analysis result on the map with 3D graphs. As you can see, this is South Korea, and over there, North Korea. The blue color, the blue color means the better quality, and the red color means the worse quality. And the graph height indicates the number of the connected people to the cell tower. And if we move the location, the updated results are updated instantly. We can see the updated 3D graphs. And also, we can choose different time. So we choose different time. You can see the updated result in real time as well. So we have another demo. This another demo shows simply the number of people in the region with different age groups. We can count people in the region with various zoom level. So we can count all the population in Korea with different age group. We can choose different age group, 10 to 20, 20 to 30, like this. In order to visualize these demos, we need to handle big data comes from our cell towers. This requires huge computation to aggregate and visualize the data. Currently, we are working on visualizing network quality prediction as well. We can visualize the predicted result. So in this talk, we'll explain how we achieve this. So our presentation is going to be like this. First, I'm going to cover network quality analysis, focusing on how we solve the legacy architecture problems. And then as a result of the problem solving, I'm going to introduce a new in-memory data store for Apache Spark, which is called FlashBase, also which supports billions of partitions, and which can filter out trillion records in a second. And next, the architecture for the geospatial visualization will be explained, which is 20 times faster than the original GeoSpark. From this part on, I'm going to hand it over to my co-speaker, Tuyong. Here you are. Then he is going to introduce our network quality prediction model and our efficient data pipeline for deep learning inference, which is 40 times faster than legacy architecture. And I'll be back for wrap-up and Q&A. Okay. As I told you earlier, SK Telecom is the largest telco company in Korea. Our company has half the population of Korea as our subscribers. To support them, we have many cell towers, 300,000 cell towers nationwide. And in each cell tower, the network device which connects our people to our core network, generates a huge volume of logs in a very short time, like 10 seconds. And each log has geospatial tags, latitude and longitude associated with the cell tower's location. I joined SK Telecom in 2014, right after getting my PhD. Back then, it was big data booming days. Everybody was talking about big data, and everybody wanted to get to know Apache Hadoop and Spark. And I think we also had a big data fantasy, like we can solve any problem by using Apache Spark and Hadoop. These requirements are based on this fantasy. We need to ingest 1.4 million records per second. In other words, it becomes 120 billion records every day. And at the same time, we need to return network quality analysis result in a few seconds for specific time and for specific region. Looking back, it was very harsh requirements that we could not solve with big data technology at the time. The legacy architecture. First, we built a software stack based on Apache Hadoop and Apache Spark. And we tried to make many partitions reflecting the common query predicates, time, slots, and cell tower regions. And then we appended SSDs, which is very fast storage device, much faster than hard disk, as a block cache layer to accelerate I/O performance. And we put a lot of efforts into optimizing Hadoop and Spark to satisfy the requirements for a year. Nevertheless, it failed. Hadoop name node crashed for millions of partitions, and both ingestion and query performance could not satisfy the requirements. And we finally realized that Hadoop file system is not efficient for storing many small files. And it's our new architecture. We tried to build a new data store which can support much more partitions than hard file systems. We gathered a sort of Avengers team from the best known open source software like Apache Spark for query engine and SQL interface, and Redis for DRAM key value store, Rocksdb for SSD key value store, and finally SS for main storage devices to support short latency and parallel IOs. This architecture seemed to have a great potential at the time. I thought that we could easily build a new data store by just integrating them with some glue logics. But it turned out to be very wrong. As the initial Avengers team did not get along each other, there were many problems to integrate them as one data store. So the first problem we faced was space amplification of Redis. In other words, Redis used too much memory. As you can see in this picture, when you insert a key value into Redis, Redis creates a one dict-to-entry data structure for each hash map and two Redis objects for key and value. And each consumes 24 bytes DRAM memory. First, we designed FlashBase to use the original Redis data structures, but it consumed DRAM memory too much, 4 times of input data. It was because our workloads have very small size column values like 1 byte. Still, DRAM is expensive, right? Therefore, we designed our own data structure inside Redis called column value array, which stores multiple column values in different records like C++ vector. In this way, FlashBase could reduce DRAM space usage to 1/4 of the original Redis. After that, we faced another problem, Rocksdb's write amplification. As you can see in this picture, when you put key values to Rocksdb, they first goes into the top level of the Rocksdb, and it goes to the next level and on and on. While key values are written multiple times at the same as the number of the level of the tree with larger update regions. So originally, Rocksdb wrote 40 times of input data to SSDs. So what? You know, SSDs have a limitation on the number of drive writes, meaning the more writes, the faster SSD falls. With this rate, we could use SSD for several months. It was a big problem for us. For this reason, we customized Rocksdb to avoid next level updates as much as possible. In this way, FlashBase, our new data store, reduced SSD write to 1/10 of the original Rocksdb. Okay. After handling many problems, finally we could focus on fun parts, enhancing performance. Because we have chosen the best key value store, which can store small size data very well. As a result, we could store a lot of partitions in FlashBase. FlashBase can store up to 2 billion partitions in a single node. And this number can be linearly increased with more nodes in a cluster. In contrast, hard file system can store up to 1 billion partitions in a single cluster. This is because it consumes 150 byte memory for each block and each file. Consequently, it consumes 300 gigabyte DRAM memory for 1 billion partitions. It's the cluster limit of hard file system. And as you already know, Spark provides external data source APIs, and Spark pushdowns filter predicates to the external data source using these interfaces. This is a part of our code for the data source implementation. By using pushdown filters, FlashBase first filters only satisfying partitions in multiple processes at the same time. And for those partitions only, actual scan operations are executed, only returning the records satisfying the query predicates. So this is the query example of our network quality analysis for specific time and for specific data region. There is a SQL statement. And we could finally reduce the query time for 0.1 trillion records to 1 second. With more servers, it is also possible to filter out trillions of records in a second by increasing the number of partitions. And for ingestion performance, FlashBase can ingest 500,000 records every second in a single node. And for the rest of features, you can check them in the table. And finally, in 2017, we deployed FlashBase to production. We faced a lot of bugs and engineering problems and solved these problems staying up all night, many days. It was so hard, so it was literally hell. But finally, we went through it, successfully deployed our FlashBase to our network operation supporting system. Okay, these are the results of FlashBase deployment to our network OSSs in 2017, dashboard and Jupyter Notebook with batch queries. This is still up and running, and the cluster keeps expanding in order to support our 5G network. From this part on, I'm going to hand it over to Duyang. He used to be an Android contributor, and he joined SK Telecom 1 year ago. Back then, he was a newbie in big data area, but now he has become Spark contributor. He is a very fast runner, so I personally recommend you to hire him if you're looking for good candidates, but not right now, not for the next 3 years, because we desperately need him. Okay, I'll be back for wrap-up and Q&A. Thank you.
Hi, I'm Duyang. I'm a software engineer in SK Telecom, and I'm delighted to be here today to talk to you about geospatial visualization and network quality prediction. I will talk about why we decided to develop geospatial visualization system. Since geospatial visualization requires heavy computation while aggregating GIS data, it is a good case to demonstrate real-time big data processing. For this reason, some companies demonstrated geospatial visualization to show advantage of GPU database over CPU database. We also tried it with Spark and FlashBase based on CPU performance without help of GPU. Then I will introduce our architecture of geospatial visualization. Firstly, we use Mapbox.js as for the front end. In order to render features on map, Mapbox uses vector tile, and it gets vector tile through HTTP API. To support HTTP API, we run WebServer, which builds vector tile when it receives requests from client. The WebServer builds vector tile with Spark job. Because our WebServer submits jobs to multiple Spark clusters, we also use Apache Spark to manipulate multiple Spark sessions simultaneously. In our Spark layer, we also adopt Geospark. Geospark is open source and plugin over Spark. By importing Geospark library to our Spark application can use geospatial UDFs and UDTs and predicates. For Spark data source, we use FlashBase. The geospatial objects are partitions with geohash and stored in FlashBase. Since we use FlashBase, data can be collected and analyzed simultaneously. So the problem of this architecture is long latency of HTTP API, and this causes sluggish map loading. This is because building vector tile needs heavy computations and huge shopper writing for aggregation operation. When Spark builds vector tile, geospatial objects should be aggregated grouped by each pixel. Suppose if clients try to show 20 tiles in the screen, maximum 1.3 million aggregation operations are required. Moreover, the tiles should be recalculated if users scroll maps and change zoom level. Thus, we help to optimize our performance. I will show you how how to optimize our architecture. The first way is for Spark to push down aggregation to FlashBase. In previous architecture, when Spark builds vector tile, Spark just receives raw objects and aggregate them in Spark jobs. So FlashBase should send huge data to Spark with socket connection, and shuffling data size of Spark is also very big. However, after Spark pushes down aggregation to FlashBase, Spark receives partially aggregated data from FlashBase, so the size of shuffling and computation of Spark are reduced by 1/10. The second way is for FlashBase to accelerate aggregation with vector processing. FlashBase imports Intel MKL library when executing aggregation operations. Thus, it can double its performance of aggregation. Therefore, overall performance is 20 times faster than original GeoSpark. So let me explain optimization detail. When a client requests one vector tile, this query is executed. The unfamiliar form as the vector tile AGGR is a custom predicate that we define, which contains aggregation information. The reason why we define a custom predicate is that predicates are pushed down to data source relation, so we can use them in data source RDD of FlashBase. Then we apply custom optimization rule. This rule is applied during optimization phase of Spark Catalyst, and it parses custom predicate and extracts aggregation information from it and push down them to FlashBase. And then aggregations are executed in FlashBase. The parallel level is a process count of FlashBase, and generally it is from 100 to 200 for a single server. Also, each FlashBase process accelerates aggregations using Intel MKL, as I mentioned before. So the next topic is network quality prediction. Since SK Telecom is a telecommunication company, we predict various network quality indicators for anomaly detection and real-time management. The goal of our project is to unify geospatial visualization and network prediction on Spark together, like this picture. So we have been focusing on improving deep learning model for forecasting time series data. Also, we want to improve implementation architecture and data pipeline for training and inference. In first trial, we adopted RNN model, sequence to sequence. This is because RNN type model is common solution for time series prediction. However, it was not suitable for our data. As you can see in below picture, RNN type model cannot predict sudden change of network quality. Thus, we came up with the new architecture, which is called memory augmented model. There are two inputs for this model. The first input is current, which are recent 50-minute data with 5-minute period. The second input is memory, which are previous 1 week data, which has the same time bandwidth, current and target. With these two inputs, we predict a value after 5 minutes. Current and memory input pass through two different encoders, which are defined by autoregressive term. In next step, attention scores are calculated because this model improves prediction quality using similarity between current input and memories. The attention-weighted memories are concatenated with current state vector, and they pass through fully connected layer, and we get final prediction. This is the test result of our model. Unlike RNN model, our model can predict the sudden change of network quality. Also, the prediction error was reduced by 40%. So, this is our legacy implementation architecture. At first, we export data for training and inference to CSV format from Spark Thrift server using Hive client. Then we pre-process the data with Pandas library. The training and inference are performed using TensorFlow CPU. So there are two problems in this architecture. Firstly, there is no in-memory pipeline between data source and deep learning layer. Thus, this architecture is not only bad for performance, but also difficult to update with new data. Secondly, pre-processing, inference, and training are performed in a single server. For better performance, we want to do all this together in clustered environment. Therefore, we collaborated with Intel and implemented the new architecture. We built a memory pipeline between our FlashBase and Intel Analytics View. Through this pipeline, data layer and deep learning layer are integrated into the same Spark cluster. Furthermore, pre-processing, and inference or training are executed in the same Spark job without collecting data to driver. Intel Analytics View is used to unify TensorFlow model into Spark without modification. Pre-processing job is defined as Spark RDD, and TensorFlow model is transformed into Spark broadcast value using Analytics View API. With this RDD and broadcasting model, Analytics View performs inference or training on the Intel VDL. Consequently, we can easily distribute pre-processing and deep learning processing in Spark cluster. I will compare the test result of two architecture. Now, we only tested inference, but we will also test training later. Our test data was collected from 50,000 cell towers. As you can see below table, new architecture is 45 times faster than legacy architecture. This is because pre-processing and inference are distributed across 50 partitions and executed in parallel. We also measured inference time of TensorFlow CPU and Analytics View. As you can see in below table, Analytics View is approximately 3 to 5 times faster than TensorFlow CPU in Intel devices. That's all I have to say about network quality prediction. This is an appendix topic, which is memory problem of Spark driver and how we solve it. The collect function of dataset sometimes causes out-of-memory error while decompressing result. Spark supports max result size config for memory problem of the driver, but it just limits compressed result size. We solve this problem by defining new function in dataset, which is called collectAsSeqView. The function returns sequence view of Scala that holds compressed result and decompression operation. Driver decompresses only the parts fetched by client and then collect them as garbage. Since driver can reclaim its memory by this way, we can protect the driver from out of memory. Consequently, the new function spends only 10% of memory compared to collect function. I created this pull request in Spark repository. This patch protects Thrift server from out of memory. If you are suffering from this issue, I recommend you refer to this patch. Now I'm going to hand it over to Hongchan again. He will wrap up this session, and thank you for listening.
Okay, it's me again, and I'm gonna speak about the web. So these are the discussion points. You can visit, you can give questions in the Q&A session, and you can visit our demo booth with Intel. You can talk about these topics. And if you want to try or collaborate with us, you can contact us. We are gonna release our FlashBase free binary version in Databricks by the end of this year. And we are planning to open source it. Okay, thank you.
We've got about 10 minutes for questions. So again, if you want to ask a question, just raise your hand and I'll bring the mic.
Hi, thank you for the presentation. I have a question about the memory handling. You mentioned in the deep learning algorithm refinement, you use attention layer. I saw the self-attention equations. Did you try the local attention and compare which one was faster and gave you the more accuracy and better for memory handling?
Actually, we have adopted recent deep learning model.
Okay.
But we are data engineer rather than data scientist. So for your question, I think we need to discuss in our demo booth with time. So we couldn't understand the question totally. Can you visit our demo booth, Intel, and discuss about them?
So in the comments discuss with
Yeah.
Question here.
Yeah.
I have a question. In your initial work, you have the single node and was using TensorFlow model. Mm-hmm. And then you migrated to Spark multiple node.
Right.
Then you, instead of TensorFlow, you are using Big Deal.
Right.
Is it because you cannot do the TensorFlow Spark together? I just know why you want to make a change, right?
Yeah, it's a good question. Actually, I think because we have to deliver the pre-processed data to TensorFlow or the deep learning inference processing unit. But if we want to use TensorFlow, we need to translate the format, RDD format, into TensorFlow's familiar format. There would be an overhead between them. So we decided to use native data structure. There is no conversion overhead. So we adopted Intel's Big Deal, which is based on Spark RDD's processing. There is no conversion.
Mm-hmm.
Yeah.
So let's say you could using the Apache Arrow as the common format between the Spark and the TensorFlow. Will you make the change or not?
Pardon me?
Yeah, I think it sounds like logically the challenge you face with the data exchange format, right?
Right.
I think there's some discussion about using the Apache Arrow as the data exchange format as a part of the project Hydrogen.
Yeah.
Thank you.
Thank you.
All right. Thank you for the presentation. The question is, how did the introduction of this solution translated to business value in your telecommunications sector?
Because we are a telecommunication company, so the major business is our mobile network business. We need to support them, building better infrastructure. If we adopt a proprietary, expensive database into our infra, then we need to pay more. So we contribute our company to reduce the TCO, total cost of ownership, ownership, and we actually reduced the infra size. Actually, the hardware cluster was very big, but we just use 16 nodes for this processing right now.
Right. Thank you.
Thank you.
I have a question about the partitioning by geohash. So did you do partitioning on every level of geohash, or did you pick one specific level of geohash and then partition by that?
Good question. Actually, we first built the partitioning method based on geohash. We picked the level of the partition. But now we are developing a new technique. Actually, we have implemented that. Based on the object size of geometry data, we automatically decide the level of geohash.
Thank you.
Thank you.
Hello, pretty good talk.
Thank you.
Also on the telecom side, so I was just wondering, what were you predicting? Radio conditions, like?
Radio network quality. You know, our network guy defined some measure based on the key index attributes, like RSIP, RSIQ.
Okay, so you built a kind of indicator, a custom one.
Yeah.
Okay.
On our own.
CQI, RSSI.
Yeah, like that.
Oh, okay. Radio conditions, specific one.
Yeah.
Okay, thank you for that.
Thank you.